Hello everyone, welcome to the channel Top Gate. In this video, we'll discuss first come first served scheduling algorithm, and in the previous video we have already discussed what is CPU scheduling. We have seen what is the difference between the preemptive and non-preemptive scheduling, and we have also seen the scheduling criteria of the CPU scheduling. Fine. So in this one, we'll start with the very first algorithm that is called as the FCFS algorithm. That is a very basic and very simple algorithm, and this algorithm is asked in almost all the university exams, and it has been various times it has been asked in the GATE exams and NET exams and various competitive exams as well. So let's start with this algorithm. In this algorithm, first of all, I'll try to explain you what is this algorithm all about, and then I'll try to explain you with the help of an example. Fine. So let's try to understand this with the help of these four simple points. It says, the first point says that it is a non-preemptive scheduling algorithm. So we have already seen that there are two kinds of algorithms. One is a preemptive algorithm and one is a non-preemptive algorithm. The non-preemptive algorithm are those algorithms in which when the process comes on the CPU, the process will not leave the CPU unless and until its work is completed. That is, no process can forcefully take the CPU from any other ongoing process. Clear? So it is a non-preemptive scheduling algorithm. Will only schedule those processes which are non-preemptive in nature. Fine. Second point, it is a very simple algorithm, very simple to implement. Fine. And the fourth point says that it uses queue data structure. Clear? So what is queue? Queue is whatever process is arriving first, we will be scheduling that process first. So the basic idea behind this algorithm is that we will be scheduling that process first which is coming into the RAM first. So let's start with the example. We have this example. In this one we have 6 processes, P1, P2, P3, P4, P5, P6, and the arrival times are given as this, the burst times given as this. So I'll not explain to you what is arrival time, what is burst time, that we have already discussed in the previous lecture. What is arrival time, what is burst time. So you can go to that lecture and you can see what is arrival time and burst time. Fine. So in this one, the most important thing is the arrival time. So we'll only stick to arrival time. So we'll schedule the processes with respect to the arrival times, not with respect to the burst times. Fine. So burst time will be used, of course, but the most important thing is the arrival time. We'll see in this one. Clear? So let's start with the algorithm, and in this one, when we are solving this numerical, the first thing that we have to do is we have to make the Gantt chart. Okay, so Gantt chart is nothing, it's just a schedule of the CPU. That is, it's just the timeline of the CPU, how the process are getting executed on the CPU. That is just a timeline called as the Gantt chart. Fine. So first of all, we'll make the Gantt chart, and that is the most important thing. And if we make the Gantt chart correctly, then we can, with the help of the Gantt chart, we can calculate the wait time and the turnaround time. And the wait time, turnaround time we have already discussed in the previous lecture. Fine. So let's start with the Gantt chart. So what we'll do, we'll make a Gantt chart. Okay, so Gantt chart is just a schedule, is just a timeline of the CPU. So we'll start the timeline of the CPU from point number 0. So point number 0 means, time 0 means currently the time in the CPU is 0. Fine. And we'll see that what are the processes which are coming into the RAM at point 0. Now just make this thing very clear into your mind, that this arrival time is the time at which the process is coming into the RAM, and this time is the time at which the process is coming onto the CPU. Fine. So this is the time for the process to come at the CPU. This is the time for the process to come in the RAM. So these are two different things. Fine. So we'll see at time 0 what are the processes which are there in the RAM. So out of these 6 processes, we can see that P6 is the process, is the only process which is coming onto the RAM at time 0. So at time 0 we don't have any other option, we only have one option, P6. So we have to schedule it, and the algorithm says that it will schedule that process first which is coming into the RAM first. Fine. So at time 0, P6 will start, and P6 will try for how many units? For one time unit, because the burst time of P6 is 1. So it will start at 0 and it will complete its work at point number 1, and no process will be able to preempt this process P6. Why? Because we are following the non-preemptive approach. Fine. So P6 will start at 0 and it will complete its work as at 1. So this process is completed now. So it will terminate. Whatever allocations have been done will be deallocated now. Fine. Now this process does not exist in the RAM at all. Clear? Now we are at time 1 and we'll see that at time 1 what are the processes which are there in the RAM. So we can see that there is no process which is there in the RAM. So if there is no process, we don't have any other option. We have to keep our CPU idle. However, we don't want our CPUs to sit idle, but since in this case we don't have any other option, so we cannot do anything. Therefore the CPU will sit idle for how many units? We can see that the next process which is coming here is at time 2. So from 1 to 2 the CPU will sit idle. Clear? Now we are at time 2 and we'll see that at time 2 what are the processes which are coming there in the RAM. So we can see that P4 and P5 both are coming at time 2. So there is a tie in this case, that is P4 and P5 both are coming at time 2 and we have to schedule it. So there is no problem in this case. We can either schedule P4 also or we can schedule P5. There is no problem in that one, but the basic approach in this one is that we will schedule that process first which is written first, or we'll schedule that process first whose process ID is the smallest. Right? So the process ID of P4 is smallest, or out of P4, P5, P4 is written first, therefore we will schedule P4 first. However, there is no harm if we schedule P5 also at this point. We can schedule P5 also, we can schedule P4 also. So let's schedule P4 now. So we'll schedule P4, and this, since it is a non-preemptive algorithm, so therefore P4 will start at 2 and it will complete its work at time 5. That is, it will execute for its whole 3 time units. So this P4 has also completed its work and it will also terminate and it will go out of the RAM. Now at this point we are at time 5. At time 5 we will see what are the processes which are there in the RAM. So we can see P5, it came at point number 2, P3 it came at 4, P2 it came at 5. So at 5 we have 3 processes in the RAM, P5, P3, P2. So out of these 3 we have to schedule that process first which is the senior one, most senior one, which is waiting in the RAM since long. So we can see that P5 came at 2, it is the most senior one, therefore we'll schedule P5 first. So we'll start with P5 and the burst time of P5 is 4, so it will start at 5 and it will complete its work at 9. So this P5 will also complete its work, it will also terminate and it will go out of the RAM. Fine. Now we are at time 9 and we'll see that at time 9 what are the processes which are there in the RAM. So we can see that there is P3 which came at 4, there is P2 which came at 5, there is P1 which came at 6. And we are at time 9. So all these 3 processes have already arrived in the RAM, but the common approach is that we will, out of these 3, we will schedule that process first which came first, which is the senior one. So out of these 3, P3 is the senior one. So we'll start with P3, and P3 needs 4 time unit on the CPU, therefore it will start at 9 and it will complete its work at 13. So this P3 is also done and it will also terminate. Now the next one we have P2 and P1. So out of P2 and P1, which one is the senior? So I think P2 is the senior one. So P2 will start at point number 13, and since it requires 6 time units, so it will start at 13, complete its work at 19. So this is also done and it will also terminate. Now the last one, the last process is P1, which needs 2 time units on the CPU. So it will start at 19 and it will complete its work at 21. And we are done. So this is the Gantt chart, and if we make the Gantt chart correctly, then after this we can calculate every value correctly. So this is the Gantt chart. Now let's start with the calculation of the waiting time and the turnaround time. So waiting time we'll calculate. So waiting time is very simple thing. We have to calculate waiting time by the time for which the process waited in the RAM for its turn. So we'll see the time at which the process came on the CPU minus the time at which the process arrived in the RAM. That will be the waiting time. That is the process, suppose P1 came in the RAM at point number 6, but on the CPU it is coming at point number 19. So the wait time will be 19 minus 6. So we'll calculate this way. So let's see this one, the P1. So P1, the arrival time of P1 is 6, and on the CPU it is coming at 19. So 19 minus 6. 19 minus 6 is equal to 13. Done. P2, it arrived in the RAM at 5, and on the CPU it came at 13. So 13 minus 5. So 13 minus 5 is equal to, I think it is 8. Next one, P3 arrived in the RAM at time 4, and on the CPU it came at 9. So 9 minus 4, it is 9 minus 4 is equal to 5. Then P4 in the RAM it came at time 2, and in the CPU it came at time 2. So 2 minus 2. So it is 2 minus 2 is equal to 0. So P2 did not wait for even a single second also. Clear? Now the next one is P5. P5 arrived in the RAM at point number 2, and on the CPU it came at 5. So 5 minus 2. So 5 minus 2 is equal to 3. Clear? And the last one, P6 came in the RAM at time 0. On the CPU it also came at 0. So 0 minus 0 is equal to 0. So that is the waiting time of all the processes. So let's calculate the average waiting time. So average waiting time is, we have 13 plus 8 plus 5 plus 0 plus 3 plus 0 divided by, we have 6 process, 6. So if we calculate this, so it will give you 13 plus 8 is 21, 21 plus 5 is 26, 26 plus 3 is 29. So it is 29 divided by 6. That will give you 4.83. So 4.83 is your average waiting time. Fine. Now the next one is the turnaround time. So before calculating the average turnaround time, we'll first calculate the turnaround time of every process, that is P1 to P6, and then finally we'll calculate what is the average turnaround time. So the turnaround time of P1 is equal to, so the turnaround time of the process is basically, it is the time for which the process executed on the CPU plus the time the process waited in the RAM. That is, we'll add the waiting time and the burst time. So for P1, what is the waiting time? So for P1, the waiting time is 13. So 13, in 13, we'll simply add the burst time. The burst time of P1 is 2. So 13 plus 2 is, it is 15. Of P2, for P2, the waiting time is 8 plus the burst time of P2 is 6. So 8 plus 6, that will give me 14. Then P3, so for P3 the wait time is 5 and the burst time of P3 is 4. So 5 plus 4 is 9. For P4 the wait time is 0 and the burst time of P4 is 3. So 0 plus 3 will give me 3. Then P5, the P5's wait time is 3 and the burst time of P5 is 4. That will give me 3 plus 4 is 7. And the last one, P6, the wait time of P6 is 0 and the burst time of P6 is 1. So 0 plus 1, that will give me 1. Fine. Now the average turnaround time will be, average turnaround time is equal to, we'll add up all these values, that is 15 plus 14 plus 9 plus 3 plus 7 plus 1 divided by the number of process, that is 6. So 15 plus 14, it is 29. 29 plus 9, it is 38. 38 plus 3 is 41. 41 plus 7 is 48. And 48 plus 1 is 49. So it is 49 divided by 6. Say 8.166. Fine. So 8.166 is your average turnaround time and 4.83 is your average waiting time. So hope this algorithm and this example is clear to you, and in the next upcoming videos we'll be discussing 1 or 2 more examples of this FCFS algorithm, and as well as I'll be discussing what is the problems that are associated with this algorithm. Thank you so much.